So if you take a very broad look at the field, like almost go back 50 years, this is where like a scientific computing and high performance computing started. Then in another like 25 years, big data analytics came, like we had access to data. So then how you combine the data and the compute. And then in another 10 years, of course, the field of AI came, the machine learning. And now what is happening, I mean, of course, we are in this AI world, but there is a little bit of difference. Something new is happening, and this is what some of you must have heard of called computing continuum. Okay, what does that mean? So here, if you take a look at the left-hand side, so this is our traditional way of performing HPC, AI, or big data. That means you get the data, you put it in some file system or centralized server or in the cloud, and then operate it. But if you see on the right-hand side, this is where a lot of new kinds of actions are happening. These days, the data is coming from all different devices. It could be coming from sensors, it could be coming from drones, medical instruments. And while the data is coming, we also want to operate on those. And when I say operate, that means the same like AI, big data, HPC, everything is free. So this is where the new field is coming. So what I'll try to do, there will be two parts of my talk. I'll first focus on the left-hand side. That's what I've been working for the last 30 years. And then the right-hand side, this is where the new, one of the NSF AI Institute I am leading called Icicle, and that is purely focusing on this. And I'll show you how the things are being transitioned from the left side to the right side. So the broad challenge, if you take this entire field, how do you design this high performance and scalable middleware? Okay. With all the different kinds of devices, when I say devices, it could be a combination of CPUs, GPUs, edge devices. People are also talking about some new devices called DPU, data center processing unit, IPU, HPU, and also cloud resources. So in this context, another thing what is happening is like there is a convergence what is happening between HPC, AI, and DPU. Earlier, like they were all separate, but irrespective of what you operate on, just because of the data, just because of the computing need, you cannot solve this on a single node. Okay. Might be if you have a small data set, laptop is good, or one server is good, or one GPU is good. But when you are trying to extend that into petabytes of data, you need scale up. That means within the node, you need to keep on adding more CPUs, more GPUs, as the system allows. Most of the time these days, you can go on some modern servers, 8 GPUs, maximum 16, but you cannot go beyond that, okay, because of the physical limitation. And then you have to actually scale it out to might be thousands of GPUs, okay, or even 10,000s of things. So you need to go this scale out, and in order to achieve that, you need a good underlying runtime, purely for computing. And this is where I'll try to show you, and we have been working. Can that runtime be NPI? NPI is like a message passing interface. If some of you know, it has been there for many, many years. And most of the HPC applications run. And I'll try to show you what we have done. Now we have linked even the AI workload to NPI. You can run actually distributed Python over NPI, Spark over NPI, Dask over NPI. So all these things, so if you do it, then that leads to convergent software stack. And also we can provide vendor neutrality. And I'll try to go into that a little bit more details. So this is how the talk will be organized. I'll start with this, the first project, and that is NPI library project. Some of you might have heard of it. If not, I'll introduce. That is almost, I'm running it for like 25 years. So then I'll try to go into high performance deep learning and machine learning, the project called HiDL, both focusing on training, fine tuning, inference. Then I'll go into this HiDL project, how to accelerate Spark and data science applications with Dask. And then I'll come to this, the computing continuum, which is the overview of the Icicle NSF AI Institute, and then I'll come. So this is the project. How many of you heard of this? Okay, some of you. So I started this project almost year 2000. Okay, when Infiniment came. How many of you know Infiniment? Okay, so Infiniment came in the year 2000. And prior to that, I was working on communication runtime for Mirinet quadrants, which some of the old timers are there. So heard of these technologies. When Infiniment came in 2000, it just came as a hardware, but nobody knew how to really utilize it for HPC. So I'm very proud. I was at the right time and the right, say in the space and time continuum. We were the very first one in the world to jump into this field. And we had a first high performance API library running over InfiniBand, and we demonstrated it in 2000, supercomputing 2002. Okay, just within 18 months, we had an API library which was running. And that time, of course, the latency was like 10 microseconds. Node to node. I mean, these days, of course, it's less than 1 microsecond. So I'm very fortunate. I'm proud of my team. We have been working on this project for 23 years. You know, a lot of people have talked about sustainability and all these things for projects. So this is a concrete example of how we have been running it for 23 years. And it's not just InfiniBand, we have expanded to all the interconnects. Omnipath, Ethernet IOR, Rocky, AWS EFA, OPX, Broadcom Rocky, Intel. You name any HPC interconnect, our software will run. In a vendor neutral manner, I will go into more details and giving you the best performance and scalable. Okay. And of course, there are a lot of different versions, and support the latest version supports MPI, the very latest MPI 4.1 standard. We also introduced, when MPI library came, people didn't know how to measure MPI performance. People knew how to measure application level performance, but not MPI, like how much sent takes, how much receive takes, how do you design the underlying system. So we introduced something called OISU microbenchmarks, OISU MPI microbenchmarks, and that is also exhaustively used all over the world. Any paper you see MPI, HPC, you go there and people will be referencing to our OISU microbenchmarks. So we have standardized that. In fact, a lot of procurement, if you look at the document, they say, okay, refer the OISU microbenchmarks. Of course, we have also evolved over the last 20 years. Different vendors say, they always try to manipulate the benchmarks. That's what we were telling. We try to standardize it. Some vendors don't like it, but that is left to them. We try to standardize in the most common manner so that everybody can reproduce it. And that's what we do. Every time we add a new feature to our MPI library, we also push the OISU microbenchmarks so that people can actually reproduce it themselves instead of me just telling them what's. And I'm very, again, proud. Currently, this software stack is being used by 3,400 organizations in 92 countries. Okay. If you just go to that, there is a MAP page, that link, there is a users tab, and these are the registries. A lot of people download without identifying them, Gmail, Hotmail, and all. We still allow them to download. But those who are registered, we put them on the website, okay, just to indicate without an email address or anything, just the organization. I'm sure I think Cardiff is there. I think you'll see somebody is using there. I mean, a lot of systems in UK. If you take a look at the user list, it totally spans all different countries, all different kinds of aspects. To talk about medicine, to space, to even nuclear simulation, everything is running. And all the other fields, people are using it. So when I say organizations, so it could be like, let's say in the US, think of like a Texas Advanced Computing Center is listed as one organization. When you go, they have 10,000 users. So all those 10,000 users are using our library. So literally every day, I can just estimate hundreds of thousands of people are using this library. And we are helping to advance the research in their research, not just from this. It could be mechanical engineering, it could be aeronautical, it could be astronomy, but we are trying to advance their science. And just from our site, we have crossed 1.82 million downloads, just from our website. Of course, our library is a part of Red Hat, SUSE, Stack, OpenHPC. It's very hard to keep track of those downloads. A lot of vendor libraries also, they copy from our code. That's also okay. Every time we make a release, you will see in 6 months, the same features are being reflected in Intel MPI, OpenMPI, XP MPI, Play MPI. You will see the same features are coming. That's okay. Because what we are trying to lead, and the broad objective is, of course, to really innovate. Okay, so that is the main point. And we also work with a lot of like a top 500 systems for more than 20 years. So this is how you can see how the project has evolved over the years, just purely from the download service. But this is the overall architecture. So we have systematically designed this architecture. So the left-hand side here is all the networking technologies, the features. These are all the multi-core, many-core CPU, GPU architectures. We started with this MPI for several years in the past, like there was a lot of momentum for the PGAS, Programmable Partition Global Address Space. So we also did that, but that has gradually died down. But earlier it was HPC, now we have added deep learning, machine learning, big data, data science. But the main thing is the core here. Okay? how exactly you use or optimize this point-to-point operation, you said RDNA and all, those were our very earliest work. How do you take advantage of the RDNA? Not only for point-to-point, collective, GPU. So we are continuously innovating. Every time a new network technology comes, we are the very first ones to jump into. We have a paper, and in 3 to 6 months, once the paper gets accepted, we push the design into the production. So literally in my lab, we have 200 servers continuously running QA tests. Okay, so there are a lot of full-time staff people, there are students who do the research, but they all work together with the software engineers, and we go through very production-oriented testing to make sure that the code is stable, and then we make it release, and then people can just download and out of the box it gives you performance. What I like to show. It's not easy for an academia to do these kind of things, but I'm very fortunate. We get a lot of funding from not only federal agencies, but also from a lot of companies to make it available to the audience. So originally, this is what I was telling, like we try to target like CPUs, GPUs, DPUs, interconnect for high performance computing. But because the newer workloads like AI, deep learning, machine learning, big data, data science, now we have tried to link so that people can have this converged software stack. And as long as our MRP's library runs on a system, you should be able to try to target all these work, or even a mixed work. Like sometimes in these modern workflows, you are not restricted to only HPC. Sometimes you do data collection. You run some pre-processing using your data science or Spark. Then you try to go through a model training. You will use it. Then you try to do inference. So everything you can actually do within our lab. And this is where we try to give you the best scaling and performance portability. And then what is coming, this is like very important, is the vendor neutrality I mentioned. If you take a look at the current landscape of all the clusters, because clusters are commodity, there are so many combinations. If you just take CPUs, currently in the market, there are 3 broad CPU architecture like this: x86 Intel, x86 AMD, and ARM. Okay? 3 major ones. Now talk about the GPUs, there are 3 major again: NVIDIA, AMD, and then Intel. And then interconnects, there are 4: InfiniBand, Slingshot, Rocky, and then the only pathways. So to do a quick math, that is 36 combinations. Okay. So now, of course, for a given vendor, their objective is to have that machine just give the best performance. Okay, like the combination of CPU, GPU, and interconnect. As soon as somebody outside they deploy a different combination, that performance will be gone. Okay, so of course the vendors try to give you the same exact configuration, but then that tries to lock. Okay, so whereas we are working on a very independent manner. Okay, so I'll show you. That's where the performance difference comes in. And then we also provide unified support for on-premise and cloud. We had the discussion with Omar. Gradually, the cloud is also coming up, at least their HPC instances. They are coming very similar to HPC. Okay, but of course, there are costs, varies, and all those things. So many of our designs can actually transparently work on our setup. So let me talk a little bit, go into more details. This is our latest release. As you said, like August, we made a beta release. This is the RC1, and GA will be coming out. This supports all the MPI 4.1 standard. It supports, again, all these interconnect. Even I'll talk about a little bit about the GPU side. We have very new designs called on-the-fly compression. And then I'll talk about all these additional modules which you can actually download. So we have the main module. Then you can download your MPI for DL or MPI for QML, MPI for Spark, MPI for DAS, depending on your need. And then that will give you the complete solution for your AI needs or the big data needs. So let's take a look at some sample numbers. Okay, and I took, there are 2 numbers here. One is the frontier at Oak Ridge National Labs. Many of you might be knowing that's the current number 1 system in the world, the top 500. And the second one is the Islamabad AI, the Bristol, not very far from here. So we've been working with them. And if you see see the differences. So the first one is like AMD CPU, AMD GPU, and then Slingshot. Okay, that's one of those 36 combinations. The second one is another combination, which is a Grace ARM CPU, Hopper, which is NVIDIA GPUs, and also Slingshot. Okay. So I'll try to show you these performance numbers on these. So this is the crane pitch on the frontier. I don't want to go into very details, but these are some standard OSU micro benchmarks. Okay. You can actually reproduce. So the blue one is crane pitch, the red one is our MI pitch. So as you can see, so this is the intra-node. Okay, like within the node, we start to do always systematic design, the CPU to CPU, how quickly it can communicate from the course. So as you can see, we are performing far better than Cram is like a 39%, 37%. So when you increase like a bandwidth, the higher is better, latency lower is better. So as you can see, systematically we can give you like a 30% benefit compared to Cram, which is a vendor proprietary library for that system. So this is what I was telling, like it's a $200 million machine, and it's a US taxpayers' money. But when it comes to the end users, they are not harnessing the power. Okay. So recently, the last time I was telling, like the summit, they suspended my account because I started showing this kind of numbers. They were not very happy. Okay. But recently, they have tried to, on the summit, on the frontier system, they are allowing for us to provide a module to. Okay. So it's called user supplied module, so that end users can actually take advantage of it. So that's what we are trying to deploy. So those are point-to-point communication. Then a lot of these HPC systems, and in fact, in the AI workload these days, the collectives are playing a very big role. Okay. Collectives, if you go through like any AI training, below you actually use all reduce, all to all, reduce scatter. And these are the algorithms. Vendors are coming up with their library. If you go to NVIDIA says, oh, I have a library called NECO. NVIDIA Collective Communication Library. AMD says, okay, I have a RITL. Intel says XACL. But they are only implementing 2 or 3 of these, and exactly for one of those 36 combinations. Okay. You go outside that, performance is very good. Whereas in our MPI has been optimizing these collectives for 30 years. Okay. So we have a lot of different algorithms based on the topology, based on the CPU speed, based on the network speed. We try to actually give you the best performance here. So that is the CPU. Then let's go to the GPU. The same thing happens. So the GPUs are also connected. You want the best performance between GPUs who are connected within the node and also across the node. And here, especially, I don't know if some of you would have heard of a terminology called CUDA-aware MPI or GPU-aware MPI. Okay. So this is actually the concept. In 2011, in our group, we produced the first paper and presented it at ISC. There was a collaboration with also NVIDIA and Mellons. That time they were separate. So the idea is that, let's say I have a GPU. Most of the time in the GPU, you should have done some programming. You do a CUDA copy, take the data to the host, and then you do an API send, the other side API receive, and then you do a CUDA. So that's how you move data between GPU to GPU. But then if you're using very large messages, it's not good. You go through so many hops. Okay. So what we came up with an idea at that time is that because InfiniBand and GPU adapters are sitting next to each other, why take it through the host? We can directly push it through the InfiniBand adapter and switches, and it will reach the other. So that cuts down a lot of overhead from the CPU side, and that's called GPU Direct RDMA or called GDR. We work with there, and then since 2011, not only like we have been continuously moving, but also a lot of other API libraries and AI workload, all those libraries are also. And this is what you see the benefits. And it depends on that design again, how tight integration we do. Okay. So this is what in our group, based on the message size, based on the network speed, based on the GPU speed, you can actually do a lot of optimizations. That's what you see reflecting here, like almost different kinds of performance you see here. So this is also the same, like a map on the frontier. As you can see, these are again the collectives. You get like a 50-60% benefits. So this is the very latest Eisenhower system. I don't know how many of you use this or plan to use it. So this is the new system they got last year, and now they are deploying the Eisenhower 3, which will be coming the multiple of these Grace nodes. So we have been working with them, and actually we have given a version to them. Okay. Even in the very beginning, when I showed them these numbers, 2 months back, they said, no, we don't believe them. This is the best one we have been using. I said, no, those are not the best. These are all hybrids. So we have given them they may expose it to the end users. So exactly the same thing, just like on the frontier. So these are like you see at a 66%, 22%, even sometimes 290%, 47%. Because it depends on all different message sizes. Different message sizes, how much optimizations you do to get this performance. And so that is the CPU. So similar kind of things, GPU. So this is, as you can see, like a GPU-direct RDMA. See, we can actually, within 2 GPUs, we can transfer it almost like a 3.5 microsecond, whereas CRE takes 15 microseconds. Small messages for sure. And even for the larger messages, we are able to give you like almost 30 minutes. And same thing for the collectives, like a 54%, 63%. So then, of course, you can say, okay, yeah, these are micro benchmarks. What happens to application? But it depends on the application, how much you are invoking. So this is actually actual application running on the Islamabad AI. So these are called FP. So this is a high performance FFT library. As you know, a lot of applications use FFT. This is very data intensive. And this is like all to all. And exactly, we are running on the same system. This is 16 GPUs, this is 32 GPUs. And then you can see we can boost the performance by 1.76 or 1.34, depending on all different necessities. This is what the end user sees. Okay. So in fact, your jobs will be running much more like a 35% faster, 76% faster if you use our library versus the other. So that is the kind of, I'm just showing some sample numbers, but then you can take all the other systems and you will get a very similar kind of things. So just to give you a perspective, this project has been going on, like as I said, like 23 years. These are the kind of the impact we see. So this is, there's the Idaho National Lab. There's a lot of nuclear simulation. And we actually do an MHP user group conference every year in August. So we bring all our users, they talk to each other. So this was presented by INL. So I'm just taking their slide. So right hand side, if you see, this is the number like they are monitoring from 2021 numbers. So their end users were using all different library, MFH2, OpenMPI, Intel MPI, all. But starting from 2022, see that everybody moved to just based on the number of users. Okay. Because it's able to deliver better performance. And when I say performance, the end goal is to really execute it the less time. Okay. And I don't think anybody complains if your job is taking 10 minutes instead of 30 minutes. You don't want to complain, right? So that's what we see. What is happening? The more and more users are using our library. But these are really, I'm very proud. These are some of the we work very closely with Lawrence Livermore National Lab, and if you want to heard of, is one of the largest national labs, and they use them. Okay, and we actually work very closely with them. This is a 2022, I believe, NASA DART mission. I don't know whether you heard of that. Like there was like a NASA actually flew a spacecraft. There was the asteroid was coming, and they were able to attack that. And these are the kind of the missions needs huge amount of simulation, and all of these simulations have been done using one. Okay, so this is how we are trying to, because if you think of like a research scientist sitting in Lawrence Livermore trying to do simulation, if it takes 1.5 hours instead of 3 hours, the mission goes much more faster kind of things. And this is where like we are able to engage with them and to make sure that they are getting the best performance and the best runtime kind of things. And the second one is the nuclear fusion. That also came towards the end of 2022, December. That also was done in the Lawrence Livermore National Lab, and that also was done with the lab. So you can just see, like I'm just giving few examples here to show the impact. And this is what I tell many times my students also. They don't understand. I mean, so they might be working on some component, but if you put it together, and this is where they see that their code is actually running on these large scale systems with million cores, and how it is impacting to advance the science. So that is just a kind of the overview on the MAP side. So then what we did is we tried to extend that into the machine learning. So this is where we have introduced kind of an additional model. Okay, so there's the base library, and you can think of these other libraries. I'll show you what we do there. And I'll try to show you some numbers. Like, the AI workload, you use all different kind of data parallelism, model parallelism, spatial parallelism, a lot of parallelisms are coming. I'll talk a little bit about the on-the-fly compression, inferencing, and then also the machine learning. So if you take a look at some of the stacks, the top level, most of the time, the intermediate ones, like people use either Python or TensorFlow. TensorFlow was older, now people have moved to Python or distributed Python. So below that, if you go, this is what I was telling, like either task distributed deep speed, somebody has to link to the underlying scale-up, scale-out library. Okay, so this is where the vendors are pushing their own library, saying, okay, with the NVIDIA, they say, okay, distributed PyTorch, you call make a library, and that's all. Okay, what we have done is modified the distributed PyTorch and DeepSpeed, and we have put it into our library, so you can do CPU training or GPU training, and these are all like a codes available in the GitHub. You can download. Anybody in like a 15-20 minutes can rewrite or put that patch, and then you are able to run without internet. In fact, if you go inside, many people talk sometimes like the DeepSpeed Microsofts, the large training, even meta training, all are now running with NVIDIA. Okay, so they're not running on the vendor library because NVIDIA always gives the best performance and scalability. So all the large training, when you say is running for 3 months, 6 months, they're all relying on NVIDIA. So then what we have done, so this is the number, this is the older number, this is the summit. This is what I was telling over, like out of the box, when the summit was installed, we were able to scale to 1500 GPU out of the box. Okay. Whereas the IBM MPI, because their proprietary library was not scaling beyond 60. And this is what I showed in the IC, and this is where like they in the very beginning they said, no, you're not reporting the correct numbers, can you give me all the waveforms? I said, yeah, these are all things. I gave it to them. And then they ran it and they actually saw this. And then that's what was leading to then they suspended my account. Okay? Because it is embarrassing for them. This is a $200 million national machine. And they're not able to, once people see this kind of numbers from outside, they get a big rattles saying, what is this doing? But again, I'm presenting numbers purely from research side. Okay? It has nothing to do with politics around. But this is what happens over the years when they start seeing this kind of numbers. So we're able to here you see ResNet with a 1.2 million messages, ResNet 50 training. That time we're able to finish in 4.5 minutes. So our system also we allow CPU based training. Okay, because you see, if you have access to a very large CPU cluster, you can still do training. Of course, NVIDIA and all, they come, no, you have to use GPUs, but each of their GPUs is like a 60K, 70K, they're rising the cost. Okay. So, whereas if you have any CPU cluster and if your like the training is not like a 6 months, 9 months, you can still use it depending on your model and all. So we support both the CPU side as well as the GPU side. So here you can see like this is running on the Texas Advanced Computing Center on 2002K CPU nodes. Each one has 56 cores. So almost like 100,000 cores, and you see very ideal thing. So this is the very latest with Intel GPUs. This is very similar to Paul's machine here, but this is running on the TAC. TAC has a very similar system with OPX, with the Omnipath Express, and with Intel GPUs. Here again, you can see compared to the very latest Intel MPI, we are able to. This is an actual application. The training is running. I told about the PyTorch and Horrible. We can boost the performance by 15%, 25% per year. Okay. Once again, the same thing happens. Like as soon as like Intel sees this kind of numbers, they suspend my account. So I get all the very many machines. But then the new machines come, they give me the access. Okay. So then the thing recently what we have done in our MPI library, which is very unique, none of the other MPI libraries have. We call something called on-the-fly computation. So this like we initiated the paper in 2021. It was the best paper finalist in IPDS, and we are continuing. So the idea is that people, like let's say the GPUs you use for whether for HPC or AI, doesn't matter. You push the data, it performs the computation, then it has to communicate. Okay? Because you need that scale up and scale. Okay? Single GPU cannot do all these things. But during the communication time, most of the time, the GPUs are idle. Yeah, unless somebody has written this upper level program in a very complicated manner. Okay? So what we try to do, since the GPU is idle, and if I have to send like a large amount of data, like let's say 32 megabytes and all, these are the newer AI workload. In the traditional HPC workload, if you go back, it used to be on 8 bytes, 16 bytes, I do and all these. Now with the modern AI, when you are trying to do the training, you are trying to do 32 megabytes, 32 gigabytes. So what we try to do, that's why we call on-the-fly computation. So that means before I send the data out of the GPU, can I use the GPU cores to do computation? Okay, there are different compression algorithms. We have tried some DFT and all different. You can do lossless, you can do lossy, and we also are trying to allow for any other to plug in their compression. And then if I can compress, depending on the data and depending on application, I can reduce the message size. And then on the other hand, you have to decompress. So there is overhead of compression and decompression, but the message size, if it can reduce based on your application, you get a boost in it. So that's what we see here. If you see the left-hand side, it's a PSDNS, which is like a fluid dynamic simulation. Actual application, fluid dynamic simulation with a GFP rate, we can, if the lower is better, we can give you like a 30% rate of execution. And the right-hand side is actually an AI workload. This was run with the Microsoft DeepSpeed, and online they're using all-to-all, which is very compute intensive. And then you can see like we are able to reduce again the training time by 20%. So this is a very novel technique which we have used. We started with the NVIDIA GPU, the very latest version has AMD GPU. We have not taken it to the Intel GPUs yet, but this is how you can also use the very latest GPU clusters to boost your performance. So those are some training. Now the thing is, this inferencing is becoming one. This is what I was telling Omar. If you think of like how many of you use ChatGPT? Some of you, like it. Okay. So if you see like any ChatGPT, whether you put it in your like iPhone or laptop or something, you will be seeing like a blink. Have you seen that? Like you put your query, after some time your response comes. Okay. So what is happening is your request is actually going to some servers, depending on how OpenAI and how they have configured it in the local per country, or it goes to their end server or your server. Now think of like your request, but millions of such requests are coming. Okay. Before, and then what happens when your requests are coming, of course, depending on the query, you have to appropriately run that model. And that model, when I say run the model, you have to actually launch that kernel into the GPU. Then only it can be activated. Okay. So if you think of a lot of these jobs are coming, you can think of like go back to job scheduling. Okay, in the traditional HPC environment, if you see like a high throughput computing, when people submit a lot of jobs, how do you schedule these jobs to run? Okay, and we took some ideas from there. So this is what exactly, this was a paper in HPC 23. So people have been using dynamic concurrent instance, and we proposed this called a temporal fusion. So basically there's a kernel which is continuously running that GPU, and then as the requests are coming, it actually tries to bring that kernel and bring the associated layer of that model together so that it can actually. So we did this. In fact, this is released already. Released it, but if you take a look at the numbers, like this, the GPT 6 billion, Llama 13 billion, and all these things, we are able to give like a 16.7x speed up compared to like what NVIDIA was trying to do. Okay. Once again, once NVIDIA looked at these numbers, once it was published, they started contacting me saying, everybody starts with saying, no, you are doing something wrong. It never happens. Okay, so we told them, they had a lot of discussion, and we even went in the presentation to GPC, and then very quickly they took the design, then put it into their latest TensorRT. Okay, TensorRT thing. So this is what is happening. Okay? So because they are engineers, so are not able to think of this kind of optimization thing. But now I think we are going into our next level. So like this, over the years, these 23 years, whenever we come up with some new designs, and then we bring it, people don't believe it, but then that is by nature, but then they understand what we are trying to do, and they take it. That's fine. So we move to the next step. So this has been our ecosystem. So that is partly inference. The same thing is happening also machine learning applications, traditional machine. Okay. So here again, NVIDIA, as I said, like they support something called nickel. We introduced some MPI for pi, and then we linked it over a MapReduce library, and look at the numbers. Like k-means, linear regression, nearest neighbors, truncated. These are the very standard machine learning algorithms, and we can give you a boost, almost 1.6x, 1.23x kind of things. And then recently we have expanded that into the big data. So there we have like two modules. One is for MPI for Spark, and another one is for MPI for Dast. So Spark, in fact, I had a project called High Performance Big Data. We started that like almost 2010. So there we had optimized Hadoop, Spark, everything for MPI. Okay. But then with all the it's the same designs you can do, but it's like not a really like a good for publications or anything. So this is where what we are now trying to boost it to the MPI. Okay. The MPI is like our currently underlying the thing. So what we did is the Spark, we connected like a going through the native through Java and AI. So we have linked it to the MPI. So then what happens, it becomes a vendor neutral design. Okay, now I don't have to optimize for each and every network. Okay, so this is where, as you can see, like MPI Spark with the very latest version, you push it. So there are 3 numbers here. There are some standard micro benchmarks. So this is our this is like a very regular Spark. You download, that only runs with TCP/IP. Okay, that can run over network. There's a module called IP over IP. This red line was our own design. Okay, but then this was already an older design 5-6 years back. Okay, but that has not taken advantage of all the RDB principles and all. Whereas the latest one, by default, we are not doing anything new. That it's just running on top of MPI and able to give you that kind of performance out of the box. And this is very interesting. This is running on the TAC system. So this is like a Frontera system. These 2 Frontera systems. But this is like a Stampede tool. It's running with Omnipath. The left towards InfiniBand, this is Omnipath. We didn't do anything for Omnipath. Okay, so that's the beauty of this design. Once I abstract it up, link it to the API layer, because MRPs is running with Omnipath, that design has been done separately at the API library layer. So now Spark is just automatically running here and giving this boost in the performance. Okay, it just runs out of the box. So this is how we are trying to provide this kind of a portability. And then this is a new data science thing coming, Dask. I don't know how many of you have used here, or this is a new Python-based environment is coming. In UK, in some of the places, I think Cambridge and all, they are doing this STAR project. Some of you must have heard of the radio telescope. There are a lot of those big data intensive applications, they're using Dask. So similar kind of things are doing. So there are solutions like a TCP layer, UCX layer, but we have linked with our MPI layer. And here you can see like on a GPU, some micro benchmarks like a 2.91 times, almost factor of 3.6 compared to what NVIDIA is trying to do website. So with this, I just want to provide like that left-hand side of the picture I started with, like to design this middleware in a vendor neutral manner and with keeping that scale up and scale out, so that any new deployment comes, you should be able to actually utilize our software. Any quick questions there?
Yes, very one quick. So the layer that sits above the Python layer, when Python talks directly to NPI, how does the connection happen between Python and NPI?
Yeah, so this is what I go back here. So this one. So always this PyTorch, below that, if you see, like it started with a robot, and then people are gradually moving with torch distributed deep split. So you can see that there is an intermediate middleware layer. So this is what industry standard is evolving. So when you use PyTorch, always below there is a distributed version of that. So what we have done is that link to them. Okay, and that's what is a small, like a program is available. You can just download and patch it. Okay, so if you have your own torch distributed, then you just patch our things. That's all. You need to nothing. The same thing we are also trying to do. So the goal is your end application, they don't have to modify nothing. You still run your own things. It is the intermediate one, it's just like in the electric outlet, Instead of connecting here, connected here. That's all. Any other questions?
Yeah, with MBOH, to what extent is it possible for an application vendor to prepare a binary which is system agnostic and then just deliver it to users to run it in a platform, maybe with a hardware discovered and then exploited properly? Is that how it works, or does it have to be either the library of the application built on the target system, maybe tuned with expertise?
No, okay, so there are multiple things here. That is a more deployment question. In fact, all the libraries, whatever I indicated here, like if you take like any of this library here, like the MRPitch version, whatever I said, some of these libraries are actually buying. Okay, we do a lot of this discovery within ourselves. Okay, so we have like a very runtime architecture detection. We detect like all the different parameters of the system, CPU, GPU, network, and all. We configure that like ourselves. So when you just download, you just link to your .xo file, then you can. So that is one. We also allow for people to actually build themselves. Okay. So many of these applications in the HPC application, as you know, there is a API compatibility to it. Okay. Might be your library is already linked to you build with OpenAPI or MPEX or with Intel API, then you run with all that. So in that ecosystem, what is happening is there is a MPEX, which is like Argon, which is a derivative of that. There is an ecosystem. They are all API compatible. Like MPEX, MapPage, and Intel API, even MPEX, all of it. Okay. So as long as you just have a module from our version, you don't have to recompile your app. Whereas the OpenAPI, which is another competition kind of thing, so they don't have the same API, but there is an initiative going on to even to have API compatibility between them. But that has not happened. Okay.
So I was really shooting at, on the big machines, there's no problem. It's likely to be expertise who know about handling pitch. But if you take a cluster component, for example, you may or may not find the expertise to actually get performance when you get pitch.
No, that's what I'm saying.
Or does it tune itself?
It will choose itself. That's what I'm saying. So what we try to do, we can work with you depending on your like a system administrators and all, how you deploy it. Most of the time, what happens is you make our library available in the module. That's all. Okay. And once that module is available, as soon as somebody logs on, they select the module. That's all. The end users don't have to see it. It's the system administrators, they need to make sure either we work with you or we have a very detailed user guide. When you don't have to talk to us, we publish that. You can take it and make it available in the module. That's all. Okay. So then let's move to the second half. So I talked about the normal thing. So this is one of the NSF AI institutes. So this is where I'll focus on how things are moving into this computing continuum. So I talked about this computing continuum. So as you can see, like depending on the scenarios, you have like a data is coming from on-field sensors. You need to take the data, or like when I say take data or results or even training, inferencing, with near edge clouds or HPC, depending on that scenario. I'll go into more details. So the challenge here happens that how do you design or create this intelligent cyber infrastructure, okay, for the computing continuum, and also how do you democratize so that more and more people can use, because that is a very vast field. There's so many different sensors, so many different drones, so many different applications, but we want people to start exploiting the performance. And this is where this NSF AI Institute was funded. If some of you know, the National Science Foundation in the US has funded 27 of such things. Each one is at 20 million. So do a math, like a US government has spent almost $500 billion, more than $500 billion to advance the AI. And all these things have happened with the competition in China. AI is going so strong in China, and US government wants to invest. So they have put 27 of such institute. I lead one of these. That's what I'll be talking bicycle. And the focus is on cyber infrastructure. So every institute has their own focus. Some of them are computational AI, some of them are ethics, some of them are trustworthy AI. So like this, everybody has a focus. And our focus is to design this middleware and this. So there is a short video here. Let me play.
A policymaker wants to know how land use policies will affect a region's biodiversity. A farmer is concerned about how new weather patterns will affect crop yield, while food distributors and public health officials are concerned with how supply chain disruptions will affect deliveries of nutritious foods to communities. Current technology can provide data and models to tackle grand challenges such as biodiversity, conservation, and agricultural and food system resilience. But it still lacks the infrastructure to link across data and models seamlessly to answer complex questions from diverse stakeholders' perspectives. Even AI experts are challenged to create standardized solutions across domains because a standardized cyber infrastructure integration with AI just doesn't exist. Enter Icicle, intelligent cyber infrastructure with computational learning in the environment. Icicle is an institute dedicated to building a national AI-driven computational infrastructure that functions as a utility, much like our electricity, water, and transportation infrastructure. This new utility will enable the delivery of AI to end users with the flick of a switch, enlightening solutions for imminent problems of national, regional, and local importance. Icicle will provide an operational rationale and framework for a cyber infrastructure that delivers wide and easy access to smart computing, plus a conversational interface that allows stakeholders from diverse domains to ask questions and receive answers informed by currently available data and knowledge. For example, food distributors, emergency food agency managers, and logistics company executives might ask, which food supply chains will likely be affected by an approaching storm? The Icicle conversation agent might respond with, I will predict future states of your regional supply chain under forecasted weather scenarios and evaluate alternative scenarios. Okay? Upon confirmation, Icicle would then retrieve satellite data on weather, connect to weather forecast models, acquire inventory data for food producers, processors, wholesalers, and retailers throughout the region, use AI models to forecast supply chain conditions from a baseline, and alternative logistics that maintain consistent food supply for vulnerable populations. Icicle holds the potential to transform today's AI landscape from a series of fragmented tools for use by a few to one where democratized AI and integrated plug-and-play architecture empower diverse end users with knowledge and data flows. Introducing AI for CI for AI. AI for everyone.
So that is kind of a very broad vision. What we are creating like the next 20 to 30 years, how this field will evolve and what is the basic cyber infrastructure pieces. So I talked about the computing continuum. So as a part of this this proposal, there was a mandate that you have to work with some use infrastructure, not just work on the ranking. So we selected 3 of these: digital agriculture, smart food sets, and animal quality. So in fact, in our team, we are not all computer scientists. We are actually working with algorithms. We are working with faculty from the agriculture department, faculty from transportation department, so that they know the domain, and then we are actually working with this. And then the middle one is actually the cyber infrastructure. So this is a very large team. OISU is the lead and the overall PI. But if you take a look, there are 16 organizations, coast to coast. There are 30 faculty, 26 staff, because one of the mandates is also to deliver software, not just IT. They were like, we got funded from Office of Advanced Cyber Infrastructure. So they want the real software to be delivered so that people can start using it. And so altogether, like around 126 people are working there, and we have a lot of collaboration with all other NSF-funded AI institutes going on. In fact, this has also gone global. We got a joint grant from Government of India on the digital agriculture, because the agriculture issue is worldwide. Okay? But the same solution may not work. Like whatever works in soybean field in Ohio will not work on the onion fields in India. So this is where like a lot of joint work is going on. So this is the kind of the overall view. These are the different components, and you heard about that conversational agent. So we want to make it all available through different apps. Okay? So for example, a farmer, I can't ask the farmer to learn Python and distribute Python, but I can convert all these things in an app, and where the farmer can actually subscribe with a $9.99 a month. So that is the kind of the vision, so that more and more people start using it. And of course, we do co-designing. And within this, of course, there are a lot of trust. Within trust, we have sub-trust. I'll not have time to go into this, but as you can see, like we have knowledge graphs, model commons, adaptive AI, federated learning, conversational AI, high performance training, data management, edge intelligence, adaptive AI. So all issues, different people are working. And then we are trying to combine all them. Not only we have the papers, but we are trying to actually combine. So these are actually the software which have been released. So we are just completing the year 3. If you go down here, You will see all the software, different color coded, component by component we are trying to release. They have not been all integrated yet. We have 2 more years to go, but already like, as you can see, like we have seeing the users starting to use it, like a 2000 clones, views, a lot of downloads are happening. So let me show you some highlights. Okay, this is a large project, will not have complete time. So the agriculture, so this is what we want to see. For example, let's say you have a big field with soybean and you want to detect in real time what kind of disease are happening. So the question is, can I fly a drone? The drone will have the AI model for that particular field and that particular disease kind of thing, or a combination of disease. And then when it is fine, depending on the drone type, how does it actually select the appropriate model, okay, which will lead to best accuracy. And then the question is, does the inference happens on the drone, or it sends the images? It can reconfigure itself, and depending on the amount of power it is needed, amount of computational resources, either it can do it itself, or it can send to the cloud. But in the end, whoever triggered this mission will be able to get this kind of solutions. And then we also want to connect it to the track. The tractors and all are becoming intelligent. They have now GPUs, they have sprayers. So if you can put it there, then it can actually, the tractor can actually go and then spray exactly the amount of the fertilizer or pesticides or even water you are talking to appropriate places. So those are like a very precision digital agriculture. That's what we are trying to do. So we have developed a pipeline here. So you can think of like data collection, processing, training, inferencing, visualization with all these modules working. So let's listen to a short video.
Welcome to the future of agriculture. This is Icicle's AI cyber infrastructure for end-to-end processing of digital agriculture use cases. As a user of this framework, you can easily compose and manage your jobs all from one convenient and user-friendly interface, which is connected to an HPC backend where your jobs will be accelerated on modern GPUs and CPUs in a distributed fashion. Let's get started. The dashboard is your control center. Here you can select from many modules to compose your new jobs. Depending on the nature of your job, you can take advantage of one or a combination of modules, including data collection and preprocessing, image labeling and high-performance model training, model inference, and visualization of results. The dashboard provides a comprehensive overview of your resource usage, data storage, and processing times. Let's walk through an example of creating a job which uses all of these different modules. The use case here is classification of growth stages in a cornfield, where the goal is to train and use a deep learning model to analyze phenotypic data and provide detailed insights on the growth stage. Let's create the new job. The first stage is data collection and preprocessing, where you can import your data from Model Commons or upload it from your edge device directly. Once the preprocessing is done, we will have access to download and examine the preprocessed dataset. For now, let's move on to the next step, which is the model training. This page shows a list of model training options. The values will be populated by default for beginner users. At the same time, advanced users can adjust the training hyperparameters. The domain expert will then provide a number of labeled images for each class. This current page shows the first growth stage class, as shown in the very top. We can navigate through the samples and select representative images. Then we'll click Submit to move on to the next class to be labeled.
So might be I'll skip this. So this is where you can see, let's say these are actually running on two versions are running. One is in the web center, one is Scalable center, and we are taking to make it to cloud also. So you can bring your own data and then interact with it. And you don't have to go through all these complexity. You can do your data labeling, you can go through your training, you can do inferencing, and you can also visualize the results, how the results are. And in the end, so this is my colleague who is a drone expert. So we have actually farm. We are running it on an Oishu farm. So this is how in the end you will get a feedback. So this the field. If it's just a two color coded, it just says okay, the red ones are the disease, but you can have multiple depending on what kind of disease. This is the information you get, and then either you give it to the farmer or you give it to the farm. Okay. So that in the end you have a complete kind of solution. Similar things we are trying to do animal ecology. So this is more like, the conservation, a lot of focus is going on to understand how the animals behave in like a Kenya, all these big places. And can you also do similar kind of things like the drones flying, understand the animal behavior, and then trying to see from that animal behavior, how do we work together? So the issues are very similar. Here also you can see the same, like a model data selection, model training, MLOps for continuous, for your computing continuum. So let me play a short video here. And then.
As part of the Intelligent Cyber Infrastructure for Animal Ecology project, we are integrating a suite of cyber infrastructure components and tools into a unified web-accessible workbench. Together, these tools support activities across the computing continuum, from model discovery and training to edge deployment planning and evaluation. Researchers can search for pre-trained machine learning models that support their use case. A researcher types, "Tell me about the deployments of convolutional neural network models at Okavango Delta" into the chatbot because they are planning a camera trap field deployment near the Okavango Delta in Botswana. The chatbot returns information about two matching models, Megadetector and GoogleNet. Metadata, technical information, as well as performance metrics are returned. The Icicle Model Commons project is developing a powerful metadata catalog and knowledge graph about available machine learning models. The knowledge graph incorporates metadata about how the model was developed, as well as performance data from deployments of the model in the field. Based on the average accuracy and power consumption, the researcher selects Megadetector. To fine-tune this model and improve performance detecting the kudu species, they will need a high-quality labeled dataset. Icicle is indexing large collections of datasets to help researchers easily discover high-quality sources of data. The researcher is ready to develop.
So again, I'll skip. So this idea is very similar. Like we are trying to really help the end users. And these are like the animal ecology. They don't know about anything about computer science. But we are trying to bring everything to very easier manner to them. If they want to fly a mission, they are able to actually go to the interface and select the model, what's the power, and all those things through the model commons. So the last one is like the smart food. This is a food distribution. Okay. So here the idea is that, okay, like let's say, for example, if somebody is asking question like, who would be valuable partner or someone restaurant, some project in the river, or you ask questions like how much perishable food that originates in ecoregion can move to each other, the states east of Mississippi. So a lot of these food scientists, nutritionists, they want to understand this kind of behavior, and this requires data from a lot of number of databases. Okay, and very quickly you want to operate on these and give these results back to the end user, like the truck driver or any of the person wants to use these results. So here I'll just play it again a little bit and then we'll close.
The Visualization Studio is a user-friendly platform powered by large language models, enabling natural language queries for interacting with complex data. It offers table and graph viewers, a Sparkle editor, and a Vega Lite visualizer. Users can explore knowledge graphs through spoken or textual queries without needing technical expertise in a number of ways, using both remotely stored data as well as local data files. We'll demonstrate a few capabilities of the system. Users can input questions like, find possible collaborators that work on water quality, and receive detailed answers powered by LLMs with visualizations that explain the reasoning process. The Text-to-Sparkle query module for advanced users displays underlying code in the query. This is powered by an LLM-based generator using the same technology in the Animal Ecology project. Generated.
So this is where like a lot of like conversational AI, the LLMs, and all these things are being used in this part of the project, and that will also come to the other parts, like the digital ag and the animal ecology, which just started from there, and then it will gradually migrate. And so here again, the end goal is not just we are showing the results, but we are trying to actually go through explainability. And the AI is like it's very hard. And that's why we have all these visualizations. So end user can actually understand why I'm giving these results. Okay? So that is also a part of our thing, so that people can actually use and get the functions. So we're doing a lot of this collaboration across different institutes. These are like different institute like a food logistics, creating food access simulation. There is another image genomics. There is also IR, resilient agriculture in Iowa State University. And here I just want to indicate, Omar, we have been having some discussion. There is a pre-proposal has been submitted to UKRI. Hopefully we'll go into the next full proposal. There is also thinking taking place in India, Australia, and all. So it's a very large project, and the objective is to really collaborate all over the world. So it is no longer restricted to only US or Ohio. NSF wants it to go and go worldwide. So if there is any interest from any country, we'll be very happy to work. So with this, let me conclude here. So if you take a very broader look, the exascale systems people are talking about and the cloud, they need to be designed with a holistic view. When I say holistic, it is HPC, big data, AI, data science, and also the computer. So that's what I tried to show you. I started with the traditional HPC, AI, and big data, how the results are coming. And then I showed how these things are gradually moving into the computing continuum so that the end users can actually take advantage of this. Yeah, when I say end users, this could be again layman. It could be a truck driver versus a soft manager versus a farmer, but they will be able to utilize the AI. And that is the whole goal of this Icicle Institute. And if we can do these kind of designs, then over the next 20, 30 years, you will see the AI will be very much democratized and feasible. So with this, let me just talk a little bit like I hinted this, like we do this annual Arabic User Group Conference. Sadaf actually was one of our keynote speakers. He talked about Eisenhower system. We have a lot of all over the world. Every year we bring these people to share not only good things, bad things also. We want to hear from people. I mean, it's why these applications are not scaling, what problems you are facing. So if any one of you would like to share these kind of things in future years, just let me know. And all the slides and videos of the talks are available. I'd like to thank all our sponsors. But these are all my heroes. It's just within my group. What I presented here is like a work of 25 years. So each and every of them have contributed. And of course, many of these names you will see they are leading into all these big companies, national labs, and all. If you take a look at some of these things, even if I indicate this, if you go to MPI forum, like the standardization body, 70% of them have graduated from. Okay. So they are in all, working in all different places. Okay. I don't have any control over them, but they are in that field, like advancing into the things. And that is within my group, and this is actually all the Icicle people, 126 people. So these are my heroes. I'm just presenting, but these are the hard work. So with this, I will close here. I know I took a little bit, but if there are any quick questions, I'll be happy to answer. I'll be here for some more time. If anybody wants to have a discussion, I'll also be happy to discuss. Thank you.